So let's solve longest special path. You have a tree, and what's important to note is that the tree is rooted at node 0. And you want to return two things: the length of the longest special path and the minimum number of nodes. If we have several longest special paths, we want the longest special path with the minimum number of nodes. So what's a longest special path? If we look at the example from Leetcode, we have a graph, our tree, and we have colors on the nodes, and colors will correspond to an array called nums, and you can see the 0th index and the second index both have 2, so they are of the same color, and index 1, index 3 and index 5 are all blue on the graph. That's because they have the same value in this array. And the idea is to have a longest path, but we're not allowed paths where the color is repeating itself. Right? This is not a valid path. This, however, is a valid path. This is a valid path, etc., etc. Right? And the longest one is 6 here, but we also have a path of a length 6 here. And among the longest special paths, the two longest special paths, one of them has 2 nodes, one of them has 3 nodes. So we want to return 6, which is the longest special path, and we want to say 2, because 2 is the minimum of number of nodes among all the longest special paths. Right? So that's what we're trying to solve here. And we are looking for a big O of n solution, right? Because the constraints n can go up to 5 times 10 to the power 4, and yeah, that's it. So we want a big O of n solution, a big O n squared with time limits exceeded. Maybe n log n could work as well. Now the way to solve the problem is going to try and traverse each node at most once, right? Otherwise we would have a complexity that's too high, right? We could consider all the different paths that could exist, but I don't want to, when I'm considering this path and when I'm considering this path, I don't want to do this portion of the work twice, right? And that's a very common theme in tree exercises or graph exercises. We are going to maintain, whenever we are at a node, what's the longest path from the root to this node that is a valid path. So I explain myself here. For example, at node 1, the longest path that's valid from the root is actually the path from the root, right? So the path here will be 0, 1, and then I can continue in a sort of DFS fashion, and I'll get there, and I can update my path and say, well, my path now is 0, 1, 2. Except this is not valid, unfortunately, because in this path I would have 2 red nodes. I could say, then I want my path variable to look like this, 1, 2. But deleting from the list is not exactly the most efficient operation, right? So what we'll do is, instead of having an array of length 2 with 1 and 2, we'll just have a start variable. We'll call it whatever you want. And here start will be 0, and here start will be 1. Meaning, this is the path from the root, and start will just indicate when do I start to have a valid path. And maybe when I get to this node, our path will look like 0, 1, 2, 5. Obviously, this is not valid because 1 and 5 have the same color. So I want to have a start here that's equal to 2. And I'm going to iterate through the tree like this, and the reason why it works is whenever I'm considering the children of 5, it would be stupid not to make the path start at 2, because if I don't have anything red here or here or here, I want that 2 because I would get 6 of length, 6 additional length. And if I ever encounter a red one, well, I will just move my pointer, right? So this is why whenever I'm considering a node, I want to know from the root what's the best I could have had. Right? And there's no point in even considering any of those, because there's no longest path, special path, sorry, that would arrive at 5 and that would contain those nodes. So that's the first sort of intuition we want to have here. The second intuition we want to have is, how do we compute efficiently, right? Maybe when I'm at 5, my path looks like this, 0, 1, 2, 5, and my start is at 2. How do I compute the length of my path in big O of 1, right? Because here I only have 2 elements, but I could have 70,000 elements, and I don't want to go through this valid path and sum the weights. That wouldn't be very optimal. So what I'm going to do is, instead of having this path which is just a list of integers, I'm going to have path which will be a list of tuples. So it will be 0, 0, 1, 2, 2, 5, and 5, 11. And the idea here is the first element will be the element we had, right, the number of the nodes. And the second element will be the distance from the root. And for this, we don't care about valid special path or not. And the idea is, if I know the length from the root to 2, well, the length of my special path here is just from the root to 5 minus from the root to 2. It is the length from 2 to 5. Right? This is very similar to a prefix sum. And so we've solved this. When I have this path variable and this start variable, how do I get the length of that path efficiently? Now, for the number of nodes within that path, well, it's quite easy, right? It's just the length minus start. Right? Here the length is 4, start is 2, 4 minus 2 is 2. So obviously the number of nodes will be 2. Now, we don't want to create new lists every time we go through children, right? Because creating a list can be very expensive. Maybe I'll explain myself a bit better. Let's go back to this step. When I'm at node 1, I have 3 children to go through. And I wouldn't want to have to create, when I get there, a path variable that looks like this, 0, 1, 2. I don't write the tuples here, but we just discussed we want tuples. And another path, 0, 1, 3, and another one, 0, 1, 4. Because here, yes, it's only 2 elements that you basically duplicate, or even worse than duplicate. It could be that there's a long sort of chained linked list here that's sort of like 7,000 elements, and then you would create 3 lists with those 7,000 elements, and you would end up copying a lot of lists around, and that would be less than ideal, right? So that's very bad, and we don't want to do that. So we don't want to copy this list path every time we go to a children. So instead of copying, what else can we do? Or we can pass to the DFS our list. Right, we can say, well, keep the 0, 1 and modify it. So when I get there, path looks like 0, 1, 2. Then when I get there, it looks like 0, 1, 2, 5. And then I don't have any children left, so I'm going to backtrack, go back up. And when I go back up, so basically at the end of my DFS call, I just have to pop the last element of my path. And when I go back up again, I pop the elements. And then when I go to node 3, I can just add my 3. I don't have any children, so I go back to 1, I pop my 3, and then I can explore 4. And I get to 0, 1, 4. And that way I only pass around a reference to my list, which is very efficient. I don't do any copies. I only do appends and pops, and those operations are big O of 1. And that way, I think we covered basically the main intuition of the problem of how to get a big O of n complexity. There's one thing we didn't discuss, is how do I know when I'm exploring maybe the children here, how do I know if I'm encountering So this is a valid path. If I'm encountering a red node here, how do I know that I previously had a red node? And if I did have a red node previously, how do I modify my start? Right, and the answer here would be to use a hash map, where we map color, which is just an integer, to a node number. And we'll just call this something like last occurrence. We'll have loads of keys and values, obviously. And if I get to a red node here, I would just check if red is in this hash map, which is big of 1, and if it is, I would update the last occurrence, because the last occurrence is now here, and also the start has to move, right? Because now I'm not starting here anymore, but I'm not starting here either, right? Because I could actually consider this path. So what I have to do is just to say, well, start is now the last occurrence. There's only one O, I think, of the color I'm at, plus 1. Again, when I'm backtracking, when I'm coming back here and I want to go here, I don't want to keep the fact that last occurrence of red is this new node 6, right? Because in this path, I'm not even encountering this node, right? So similarly, I need, when I backtrack, to take care of here not popping, but replacing what I previously had in my hash map when I backtrack. And I have to do this in big of 1, and I can just pass around the reference to that dictionary, that hash map, and basically everything will go well. Yeah. It'll be clearer in the code, but at least that's the intuition. So it's a tree problem, a graph problem. So the first thing we'll do is we'll represent our graph in a data structure that's a bit better than just a list of edges, right? So we'll make a list of dictionaries. Why a list of dictionaries? Because we need to store the weights, right? This list will be just the neighbors of the given node, and for each neighbor we want to associate a weight. So for u, v, w in edges graph, u, v, w, equals w, and vice versa. And then we said we needed a path variable, and we said we wanted a list of tuples. We wanted a last occurrence variable, which is a dictionary. We also wanted a start variable to say in this path, are we actually, the longest special path, when does it actually start? When the longest valid special path actually starts. And we'll do a DFS call, and in this DFS call we want the node we're at, its index. We want to know the parent, because we don't want, when we look at the children, we don't want to iterate through the parents. I say parents with nest, but we don't want to go back to the parent basically when we do the for neighbor in graph view. So parent will be an integer as well, and also we want the distance, but this distance is this distance from the root. Distance from root. So basically the distance from the root to you, and in that distance variable we don't consider the validity of a special path or not. We'll just do, as we said, this distance minus the distance to start, to have the distance of the longest valid special path. And this does not return anything. Right? And we want to call at the end DFS 0 minus 1, because the root does not have any parents, and a distance from root of 0. And we want to initialize two variables, the longest length, which is initially minus infinity, and the minimum number of nodes, which is initially tensor of 9 or plus infinity. We call DFS here, and then we will return longest length, minimum number of nodes. Actually, let's make sure. We want the length and then the minimum, the length and the minimum. Okay. So So now we have to code this DFS. The first thing we'll do is we'll check if we've seen the color of view previously. So basically, if nums u, which is the color of view, in last occurrence, we want to do stuff, right? We want to be careful because we want to update the special path. But we want to update maybe path, we want to update the start variable, we want to update last occurrence, but at the end we said we want to backtrack everything so that we can, when we come back to the parent of u and we look at other children of the parent of u, we get the variables the way they were. So we need to have a variable which is old nums u last occurrence, which is, we'll put it to -1, which means we had not seen it, so we don't need to do anything to put it back in the same state. And if it is in it, then we'll update it to, well, the actual value. So that at the end I can say if all nums u last occurrence different than -1, I have to put back the initial value. Right, it's just to make myself clear. And we'll do the same with start and path and everything else, don't worry. So if it was in last occurrence, we need to say, well, we need to update this special path variable, this path variable, and the longest special path starts at start. So we need to move the start up, right? And what I said was I need to say start equals last occurrence, nums u +1. Here, pretty sure it complains because I will need to say that I'm actually referring to the variable that's outside of scope. So I need to write this. And the problem here is, well, I've lost track of start, of what was inside start before I've updated it. So I need to do the same. I need to say old start is -1, and old start equals start, and then I can update it. And then at the end, if old start different than -1, it means I've updated it, so I need to say start equals old start. The only problem here is, what if I've seen the color of u, nums u, but before start? So basically, what if maybe my path is 1, 2, 3, 4, 5, start is 2, so start is here, and I want to add a new node 6 that has the same color as 1. Because the start is here, it's perfectly fine, I don't have to do anything. And here I would even say start is now last occurrence +1, so I would backtrack, I would put the start before, which makes no sense, right? So I only have to do those 2 lines of code if the last occurrence of nums u is after start. Right? Because if start is here, basically anything that's before start, I don't really care what happened there, because the path I'm actually considering is this one. I don't care. Let me put that here. I don't care about 1 and 2. But it's in between quotes. And so now I've successfully updated last occurrence. I haven't updated last occurrence. Now I can say last occurrence of nums u is length of path, right? Because I'm actually going to append something to path does append u. And we'll see. For now, let's put an integer, but keep in mind we need to put the top. So just to make things clear, that might be a -1. Now that I've moved the point of start based on the last time I've seen the color, and I've kept in mind what was the last time I've seen the color and the last start, I can update now the last time I've actually seen the color, which is the last element of path, because the last element of path is u, and I can obviously append u, right? And this is length path -1, because the last element is at index length path -1. Here, obviously, I don't want to only append the node, I want to append the node and the distance from roots, right? Because we said path is node distance from roots. And if we want to see the distance of the special path we're considering, we'll do distance from root, the last, minus distance from root to start. very, very similar to a prefix sum. So let's actually compute what I just said. Path length is distance from root to u minus distance from root to start, which is path start 1. The number of nodes is trivial, it's just the length of path minus start. This we've said a minute ago, or 10 minutes ago. Now that we've computed those, we need to update those longest length and minimum number of nodes variables. Right? So if the path length I'm currently seeing is better, so bigger than nth length, no, it's not, how did I call it? Longest length. Longest length. Then I just need to say, well, longest length is now path length. And what am I writing? Longest length. Yeah, obviously this now is just the same as the start variable. I need to say I'm modifying those variables that are after the scope. This is a Python thing, but it's not very important. So if the path length is longer than the longest length, I don't care what was previously in minimum number of nodes, right? Because remember, this is the minimum number of nodes among all the paths that are equal to longest length. Because the longest length changed, whatever I had in there, I don't care anymore, right? So I can just replace it with the only path of path length, because this is the first time I'm seeing it, so I only know about the existence of one, so the minimum number of nodes is no nodes. Alright, hopefully that makes sense. Now, if the path length is the same as longest length, this is where I'm finding a new path that is the same as the longest path, and now I can just update minimum number of nodes. Right, so I will just do minimum number of nodes is the minimum number of nodes and no nodes. So I've done remembering, backtracking, updating. The only thing that's left is traversing the graph, so basically iterating through the children, but that's the trivial part, it's just a DFS. If V is the parents, I don't want to do anything. Otherwise, I'll just call DFS on V, U, and distance from root, plus the distance on the edge, UV. And then we said if old start is not -1, we need to put it back. If old nums u last occurrence is not 1, we need to put it back. If it is -1, so that one is a bit tricky. It's a bit more tricky. This we just replace if we've moved it. If we moved it, we replace it. That's what it says. This one is if we change last occurrence, we put back the one there was before, but maybe there wasn't any last occurrence before. Maybe this is the first time I'm seeing the color green, right? And I didn't have any last occurrence of the color green. So I also need to have an else if statement here. Else if, or actually else, if all nums u last occurrence is 1, it means before getting to u, -1, sorry, I had never seen nums u. So I can just delete the key I've added in the dictionary. I would just do last occurrence nums u equals del. Just deleting the key, sorry. And the only thing I've forgotten now, because I've updated start, I've backtracked start, I've backtracked last occurrence, but I haven't backtracked path. Backtracking path is very easy. I've appended a thing. No matter what happens, I append one node. So I just, well, no matter what happens after the end, I pop one node, right? And this is big of 1. Everything here is big of 1, right? Except for the traversing the children. So this is the same complexity as a standard DFS, which is basically linear. So we're very happy with that. Let me see, what is this complaining? Oh, okay, I need to, it's on the list. And this should be fine. Let's see on the examples if we have the same as what Leetcode says we have. We should have, sorry, yes we do. And let's try and submit this.